So, back in December last year, I was looking around in my cupboard when I came across my really old Nintendo DSi. I mean, it's over 10 years old at this point probably, but I last used it when me and my brother homebrewed it a while back, still probably 2 or 3 years ago. Despite its age, it still works quite well, and I'd always wondered how people made games for it. I knew DevGitArm and libnds existed for C, but how do those work? And could I get by without them? Well, it turns out that DevGitArm is just a C cross-compiler targeting various Nintendo and non-Nintendo consoles, and libnds is just a helper library which allows you to call sensible functions rather than accessing simply random memory locations and write seemingly random constants. Both of these felt like something I could really do without, and I was actually planning to start work on a compiler project at the time, just to see how to build compiler backends. This seemed like a good enough test for it, so I got to work. The first thing to do was to create a compiler front end. The compiler front end is the half of the compiler which does all the basic reconstruction required on the input code to convert it into a valid abstract syntax tree. So that includes lexing, which is splitting the code into tokens, parsing, which is restructuring tokens into a tree while making sure the syntax is valid, and then the semantic analysis, which is doing checks on the abstract syntax tree to make sure that the semantics are valid. The lexing and parsing is pretty trivial. I've covered those in a previous video about building a calculator from scratch, but there's a few extra things to do. When implementing parsing, you have to pin down a syntax that you like. Now, I like C and all, but there's little doubt that C syntax kinda sucks. Declarations are different depending on the type, modifiers are name-bound, the spiral modifier application is spider thing. Function pointers so weird that they made a website literally called goshdarnfunctionpointers.com. So, no C syntax for me. This time, I'd rather go with the Odin type syntax. Their idea is really damn cool. First of all, the biggest idea is keeping things consistent across declarations of different symbols. So, all the declarations look like this. Name:type equals value. Seems simple, right? In this case, you can actually not provide the type. The declaration syntax can infer that from the value. Or sometimes you just want to reserve space for a type without giving it a value, in which case, no need to provide the value at all. Stuff can also be compile time constants easily. Just change the equal symbol to another colon. And in this case, again, since the value is mandatory, you can just remove the type. Using any of the forms for all declarations makes things consistent, be it a function, a type, or a simple value. Honestly, this syntax is so elegant that I'm not sure why more people don't use it, but I did. Along with that, I decided to do away with the spiral type modifier thing. All modifiers go before the basic type, of which there are 6 of these, which is I8, U8, I16, U16, I32, and U32. So, simply, you can declare an array of 6 pointers to 32-bit unsigned integers like this, or a pointer to an array of 6 16-bit signed integers like this. This syntax is completely unambiguous and just better than C's. Anyways, enough of the syntax. The next major step is semantic analysis, or in my case, literally just type checking. Yeah, I didn't do much about type checking in my previous projects, so this time it was a real struggle. Let me explain. On the surface, type checking is incredibly simple. Imagine yourself going through a program and replacing every basic expression with its corresponding type. Numbers become int, string literal becomes string, compound or array literals become their corresponding type. Now we go up a level and figure out the types of expressions that are one level above the basic, that depend only on the basic expressions. We repeat this until we reach the statement level. If at any point an expression or statement expects certain types and that type is not what you get, that is a type error. Since we get our program in the form of an AST from the parser, seems pretty easy to do all this through a simple depth-first search, right? Well, not really. Even the first part of this process was oversimplified. For numbers and strings, yeah, figuring out the type of the expression is pretty easy, but we also have names, or rather variables. For local variables though, the solution is easy. Whenever you come across a local declaration, you can register the name with a corresponding type into what's called a symbol table, though in my case it's just an array. Now it's done, right? We could just look it up from the table. What else could possibly... Yeah, globals are not like locals. Unless you go with C's weird forward declaration aspect, the global scope is typically out of order. You could go ahead saying screw that, just do without, but then many things that should be possible become impossible, like calling in cycles, like so. Not just that, but even for cyclic definitions of types. You might think that that's a contrived example, but I'm using it a lot in my compiler. The first implementation of the checker I wrote absolutely ignored this, so I had to restart pretty much from scratch. This time, I asked Negate, who's really far more experienced than me when it comes to compilers. He's building his own superfast optimizing C compiler called Quick. Check it out. In any case, he gave me a few ideas. Firstly, all top-level declarations can be thought of in a form of a directed graph, where the nodes are the declarations themselves and the edges indicate dependencies. Now, this isn't the true graph. Every function is split into two parts, the prototype and the body. The prototype is analogous to the forward declarations in C. So, in reality, this graph is actually this. There's also implicit dependencies here. The body of a function always depends on its prototype. Now, there's even more special cases to building this graph. Not all identifiers you see will actually be dependencies. They could be local variables, or even, in this case, if I edit the ty struct to contain two pointers to f32s, then you might be surprised to see that f32 will not be a dependency of ty. I wouldn't show this edge as an actual line, but a dotted one, since the f32 is still there, but you'll see why in a bit how I do this. So, what do these dependencies mean even? Well, they tell you what other declarations have to be checked before the one you are looking at. This is useful for the algorithm that will be used for checking, but even before we get to that, this graph itself is a great way of checking for cyclic dependency errors. We can run a simple DFS cycle checking algorithm and ensure there's no cyclic dependencies. For example, here's one program which has 3 cycles. But you might be wondering, why are cycles actually errors? Why are they so bad? Well, in this case, here's the point. The main point of types and structs is so that the compiler knows how much space to allocate onto the stack. So, the baseline for a type to be quote-unquote complete is the size of the type should be well defined. However, in the case of cycles, this size becomes either 0 if there's no additional member in there, or infinite. Getting around this is quite commonly done with a pointer, which makes the size be a constant 4 or 8 bytes. This is the reason why I said if something actually holds a pointer to a certain type, the underlying type doesn't become a dependency. It's not really required to resolve the size. Now for the checking algorithm. Firstly, we add a simple status bit field to all AST nodes. We implement 2 main functions, isReady and transfer. IsReady looks at the dependency graph for the current node, and if all the dependencies are checked, marks the node as being ready to be checked. The transfer function is the one that does the actual checking. Within a single declaration, the problem reduces to a simple DFS plus symbol table idea that I came up with before. Now, how do these 2 functions even get called? Well, the core of the algorithm works with a work list. Essentially, we hold a queue of top-level declarations to be checked. In a loop, we can check whether an item is ready to be checked, and if it is, we can just transfer it and set the appropriate flag. If it is not ready because of some other declaration, then back in the queue it goes. This loop goes on until the queue is empty. One thing to note is that there's a possibility we run through the entire loop of the queue without being able to transfer anything. However, this should not happen if we did the cycle checking and errored out before, since that's pretty much the only condition when something like this could happen. As you can guess, implementing all that took a while, like 2 months, since I was actually figuring out everything as I went writing code, which did cause a bit of backtracking. But at the end, I had a type checker which actually freaking worked. The next step is the compiler backend, the part I was most excited for. Before I even started writing code, there was a lot of reading I needed to do. Most emulators for the DSi work with a specific file format whose extension is .nds. This is the NDS ROM format, and its spec is published online. Rather, calling it a spec may be too generous. I mentioned that we homebrewed our DSi, which allows us to run .nds files on the DSi as well by putting them on an SD card. So as long as I can compile my language down to an NDS file, I should be able to run programs both on the emulator as well as the actual console. So we should take a look at that NDS file spec. Well, okay, the first 30 or so bytes seem to be some boilerplate stuff, like names and codes, but here's where the magic is. An NDS has actually got 2 different microprocessors in it, an ARM9 and an ARM7 chip. The ARM9 is more modern, rather for the time, whereas the ARM7 was mainly included to keep backwards compatibility with the GBA console, since the original DS also contained a cartridge reader for GBA cartridges. I have a DSi though, which doesn't have that. It still has an ARM7 inside because many DS games use it for input handling. Anyways, since we have 2 CPUs, both of them have to be given code. ARM chips run, well, ARM machine code. Time to look into ARM assembly. So I can output an assembly file with the right bytes in the right place, use an assembler to convert this assembly file down into a binary file, and just rename the .bin to .nds. Seems pretty good. For now, I just decided to stub out the ARM7 code with an infinite loop. I wouldn't want to be using this for just a hello world. So now, here's the deal. I had an abstract syntax tree that was type checked and verified to be good, and I needed to convert it to assembly. Real compilers would go through multiple steps of processing and intermediate representations to optimize the code so that it becomes as efficient as possible. I do want to do that, but at this point in the project, I just kind of wanted something on the screen, so I decided to dumb everything down as much as possible. In this case, I skipped all the IRs and optimizations and just decided to convert the abstract syntax tree to assembly code directly. To do this, again, we have to do a post-order depth-first traversal. Post-order because we want to process the leaves of the tree first, and then the nodes, depending on the values of the leaves. Then we process each node by outputting a specific set of instructions. So let's go through how many of these nodes get lowered. The main problem to solve is passing around and processing values. In most modern CPUs, as well as the ARM chips we are working with, there are tiny storage units within the processor called registers. For ARM7 and ARM9, there are 16 registers labeled R0 to R15. Assembly instructions either move around data within registers into or out of memory from registers, compute values within registers, or just jump. So, taking a simple example of 10 plus 2, a good compiler would lower it down to this: 2 loads and then an add instruction. Or even better, the best compilers would see that this is an operation on constants and replace it by 12 at compile time. However, in the previous example, the question becomes how we come up with these registers R0 and R1. For this, we have to have something called a register allocation strategy, which can really get complicated. There's a lot to think about there, and not something that would help me get a hello world quickly. Instead, I decided to use a simple stack machine. A stack machine is really easy to operate. It operates on, well, a stack. All expressions push their values on top of the stack and consume values off of the stack. For example, a number expression pushes a number on the stack. An addition expression pops the top two items of the stack, then pushes the sum back on. This way, we don't really have to worry about register allocation or anything. Everything lives right on the stack. The way we do this is by reserving a register, namely register R13. This is common because in assembly, using the name SP is equivalent to R13, where SP stands for the stack pointer. It basically stores the current top of the stack, which we can increment, decrement to change where the values are. So we need to implement two main functions. A push function which pushes a value from a certain register to the top of the stack, as well as a pop to remove the top value from the stack and put it into a certain register. What these push and pop functions actually do will depend also on the type of the variable that you're trying to push on top of the stack or pop it from. Now, the main function that I would have to implement is lower, which just lowers a certain node down to assembly. Most lower implementations for expressions look simple. Write the node's children, pop the expressions out into certain registers, do the operation on the values, then push the result back. Looks easy enough. Now let's go further and look at statements. Statements are different to expressions because they don't produce values and therefore don't push anything onto the stack at the end. For example, an if statement node. The lower function for an if statement would first write out its condition expression, then pop it off into a certain register, and then do a branch to a different label based on it. While loops are also pretty much the same. Write the condition, pop it into a register, jump past the loop if the condition isn't met. Remember, assembly only has conditional jumps and labels. For statements like these, it's pretty trivial to get around. But one thing that does get a bit more complicated, and that is the exact next thing to add: functions. Functions were by far the most interesting thing to implement. They have a lot you need to think about. First of all, we need to be able to jump to and back from functions. Jumping to is easy with a branch instruction, but what about jumping back? We can't just add a label after the branch and jump back to that, because the function could also be called from different places. To handle this, we reserve a register R14 to act as the function return address, also called the link register. When jumping to a function, we set the LR register to the address that just passed the jump. This makes returning just become a BXLR instruction. Well, almost. This doesn't completely work, mainly because of what happens if we call a different function from within a function. For example, calling C from B, which is itself called from A. Whatever value LR has when calling B just gets overridden when calling C. Returning from C is fine, but returning from B will fail. So, I guess a single LR value isn't enough. What we can do to counteract this is push the current LR value on top of the stack whenever the function is just called, and pop it off just before returning. Now, the next thing to get to work is function arguments and local variables. We have been using them while type checking, but where do they even go? Function arguments can be pushed onto the stack when calling and popped off the stack just after the call is done. But about locals, where do they go? In C and most low-level languages, locals go on top of the stack. So, whenever we call the function, we can reserve some space for them just after the LR, that is the return address. But now the question becomes, how do we access them? How do we access these local variables and even the function arguments? We need to be able to figure out the address of a variable or the argument, but it isn't something we can do at compile time. Why is that? Well, because the same function could be called from different places, and at different places the stack looks different. Since the stack looks different, the addresses could be completely different. In this case though, we can notice something. If we choose a certain point in the stack and then look at the offsets from that point to get to certain arguments or local variables, these will always be constant. For example, take this piece of code. Taking the offset from right here in the stack, this A argument will always be -4 offset from this point, and the B variable will always be +8 offset from this point. This base pointer can also be stored and restored from the stack just like the LR register, and is referred to as the frame base pointer. Now, finally, with all this under my belt, it was time to tackle the hardest problem of them all: division. You might think I'm joking, but this seemingly easy problem did take quite a bit of fiddling around. The first problem was that ARM assembly just doesn't have a division or modulus instruction. All compilers depend upon some compiler intrinsic for division and modulus, so my first thought was I should just add that. But then, when looking at the DSi's ports, one section caught my eye: maths. The ARM9 chip has access to special addresses for doing division or remainder operators, as well as square root operations. This isn't floating point division. The DS doesn't have floating point processing. It's basic integer over integer division. Problem is, the website where I found this did not detail anything about how to use it, and Googling any form of division DS control thing gave me no hits. After a bit of tracing back dead websites though, I found a mirror of a website on GitHub which gave me what I needed. Speaking of this website, I'm just going to put it down in the description. It's probably one of the most important websites to have seen if you're doing any serious DS development. Anyways, back to the division. How do I use these addresses to get a division result? Well, it seems pretty simple. I just have to write the numerator and denominator to two different addresses, set the control, and then wait for 18 precise cycles, then read back the result. No big deal, just took 2 long days to find the damn website. Anyways, with the backend out of the way, well, a primitive form of the backend in any case, it was time to put together a little test. I really wanted to make the language print a hello world for this video, and believe it or not, it's not as easy as calling a print function with the hello world string. For one, I didn't even actually add strings to the language, and two, displaying pixels takes a bit of work. Firstly, we have to set up the top display to bitmap mode through these 3 writes. Now, the addresses 0x680000 and up act as the displayed frame buffer, with 5 bits each for blue, green, and red. Hence, every pixel is 2 bytes, leaving 1 bit unused. So, using the DSi screen resolution, if I fill up the next 256 times 192 2-byte words with 0x7EE0, we get a blue screen. Yeah, that was a mouthful to say. Anyways, we want text, and in this case, we need a font. So, rather than being normal and actually making it myself, I just yoinked it from the DSi assembly tutorial that I followed a bit online. Anyways, converting it to an array was simple. The font is very easy to use. 8x8 characters encoded with 8 bytes per character. Each byte describes a single row. A pixel is filled in if the corresponding bit is 1, otherwise it's just blank. So, after figuring all of that out, the algorithm is easy to implement. We just have to implement a function to draw a certain character and just call them one at a time and place them next to each other. After everything, I had a hello world. Well, never mind, just 1 minute. Okay, there we go. Finally, after a few bug fixes in the compiler, I had a nice looking hello world. For a pretty loose definition of nice looking, admittedly. I would have stopped here, but it's kind of anticlimactic, right? 20 minutes and 4 months of my time just for a hello world. So, I decided to instead try making a small game. And by game I mean Pong, just Pong. This video has taken too long already. The first thing to do was to make the paddles, and I thought that it would be easy, but found a pretty interesting bug. With the stack machine, I would push elements of different sizes on top of the stack, but according to ARM memory access alignment rules, I can't just do that. Every element's location has to be aligned to a boundary, which is a multiple of its size. So, if I were loading a 32-bit value, it has to be aligned to an address that is 4 bytes. Otherwise, I will just get random garbage. So, after painstakingly figuring that one out and fixing it, the rest of the process was quite smooth sailing. I added the ball, made it move around, made it bounce, and made the game stop if the ball was missed by a pedal. Finally, I had a working Pong on Nintendo DSi in 154 lines of code in total, plus a few thousand for the compiler itself, but we probably shouldn't include that. I tried loading it on the actual DSi and it worked. It just worked a lot slower. And I mean quite a lot slower. This is mainly because the current code generation is really slow with lots of unnecessary pushes and pops on the stack. So join me next time when I explore compiler optimizers and intermediate representations. But that's all for today. All in all, I'm happy with how far I've gotten, and hopefully I can upload some smaller videos before the next one so that there isn't a 6-month long wait between videos. But anyways, thanks for watching.